All right, so we just looked at and we saw what happens when an electron is excited and then it drops down and it loses energy. And it gave rise to the thought that there may be like sublevels in the orbitals that the electrons are in. In 1867 or 1868, astronomers discovered emission spectrums from gases on the surface of the sun, unmatched by known elements on Earth. So this is way back before we knew all of this. They found more on the sun. 30 years later, a chemist discovered the existence of helium on Earth, showing that Earth and the stars have elements that are in common. So now you have Heisenberg, his uncertainty. Can we say for certain where an electron is once we interact with it? To determine its location, we have changed it. So this is making up the modern day electron cloud. Basically is Heisenberg's uncertainty is you can tell where something is, you can't tell how fast it's going. But once you tell how fast, like where it is, you've actually changed where it is. You've affected it. You've caused a change by observing it. For instance, when we're looking at the gold foil experiment, shooting the alpha particles and it bouncing off, we have affected because we shot them through that gold foil. We changed what was going on to see a result. That's what his uncertainty is about. And he came up with this thing called the electron cloud model. Instead of orbits like Bohr, we have a cloud. And so these cloud orbits correspond to locations where a whole number of wavelengths occur, and it constructs an inference or interference that occurs with the electrons never losing energy. So that wavelength, us seeing those wavelengths, that's what it is standing for. And you can see like level 4 has a certain wavelength. Level 5 has a different wavelength. But when we try and do like 4.5, it doesn't match up. It doesn't like give its own wavelength. So each orbit has its own wavelength. So going farther, we're going farther and seeing farther into the atom. Dalton was just a big sphere. Then you had Thomson with the positive and the negative, and then Rutherford. So the positive, negative, the plum pudding. Then you had Rutherford with the nucleus, Bohr with the energy levels, Schrödinger, the electron cloud level. Now we have Heisenberg with orbits. So, okay, where are these electrons? Well, they have a principal energy level. There's sublevels, and then there's orbitals. That's a lot, right? We can work on this. All right, so the principal energy level, or the shell, that would be that N that keeps popping up. That N, it's whatever level it is on, is an N. And it's usually denoted by 1, 2, 3, 4, so on and so forth. The higher the number, the greater the energy, the further from the nucleus it's getting. Like which energy level is it on? So spacing between energy levels decreases as you move higher. What it means is the distance from 1 to 2 is greater than the distance from 2 to 3. Because remember, they don't want to like all go way out there. So 1 is far away, and then 2 is a little bit closer to 1, 3 is a little bit closer to 2. They don't want to go too far out. Each successive energy level will hold more electrons than the last one due to the presence of the sublevels. So the more sublevels, the more electrons it can hold. Okay. So, for example, your periodic table lists only principal energy levels. So what you're looking at, and let's see, down towards the bottom, you'll see something like that. Those are the principal energy levels that we're looking at. And looking at sulfur, we've got a 2, 8, 6. And sulfur is right here. And you'll see right there, 2, 8, and 6. Meaning the first energy level contains 2 electrons. The second one contains 8. The third level contains 6. And adding them all up, you have 16, which is equal to the number of protons in that atom. Remember, we're looking at atoms, so everything is neutral. Neutral, everything is the protons and electrons are the same. All right, so practice. Yeah, okay. How many energy levels are in a calcium atom contain electrons? How many contain? So calcium, Ca, right here, 2882. There are 4 levels that contain electrons. How many electrons are in the third energy level of a manganese? Manganese is Mn. If you're confused, definitely look at table S to find it. Mn is right here, and we are looking in the third. The third has 13. How many electrons are in the outermost shell, the last shell of bromine? Br, bromine. So looking right there, we've got the number 7. All right. So, energy sublevels. These are designated by S, P, D, and F in order of increasing energy. So, P is more than S, D is more than P, and F is more than D. All right. The number of sublevels within an energy level is equal to the number of the energy level. So, the first energy level has 1s. The second one has 2, so 2s, 2p. The third one has 3s, 3p, or 3d, 3p, 3d. And each sublevel consists of a specific number of orbitals. So an orbital. This is the region with a spherical sublevel where the electrons exist. Any orbital can hold 2 electrons. Any sublevel 1, any S sublevel has 1 orbital, and it can only hold 2. A P has 3 orbitals, because remember, 3s, 3, okay, so P has 3 orbitals. If it's got 3 orbitals, 3 times 2, that's 6 electrons. A D orbital, that holds 5 orbitals with 10 electrons. And an F holds 7 orbitals with 14 electrons. So because this gets a little bit confusing, how many orbitals go in there, I've given you this sheet. This sheet shows you that 1s holds 1 orbital. 1 has 2 in it. And then when you go to P level, P has 3 balls or 3 bubbles. That means it holds 6 electrons. Then when you go to D, there are 5. Then when you go to F, there are 7 right there. So use this to help you with your orbitals. All right, so the S orbital. Any S sublevel has 1 orbital, can hold 2 electrons, just like I showed you on here. Just 1. It is spherical in shape. This looks like a circle. All S orbitals have the same shape, but a 2s is larger than a 1s, and a 3s is bigger than a 2s, and a 4s is bigger than a 3s. Okay? So looking at this, just like I talked about, the 1s is smaller, the 2s is a little bigger because it has to encompass the 1s, same with the 3s and the 4s and the 5s, and so on. Now p orbitals, these look a little funky. Each p sublevel has 3 orbitals, so it holds up to 6 electrons. So here it is, there's your p, it holds 6. The shape of each orbital is similar but differs in spatial orientation. These orbitals add up to a spherical area. Now I know they look a little funky, but this is how they are. It's like almost like a figure 8 type thing going on. So you have one going the x-axis, one going the y-axis, and then one going the z-axis. So if I was to add them all together, it'd look like a bumpy circle. D orbitals. Okay, so these are really, really, really funky. Each D sublevel has 5 orbitals and can hold up to 10 electrons. All right, so there's lots. So there's 1, 2, 3, 4, 5 orbitals. This is where we get the orbitals. It's how many different shapes it can make. So this one looks really weird. It's got like 4 here, 4 here, 4 here, 4 here, and then that's just funky. They differ in spatial orientation except for the 5th. So you've got the Z, or sorry, the X, the Y, the flat plane of the XY on the X, and then the flat on the Y. And then you have like this weird Z1. And all of these, when you smush them together, they look like a sphere. Okay. How many electrons can be placed in the first energy level? So the first is N1. So because 1s is 2 electrons, you can only have 2. How much for the second orbital? Well, we have 2s, which gives us 2 electrons, and then we have 2p, which gives 6 electrons, meaning a total of 8 can fit in that last into the second. Now the third we have an S, P, and D. S is 2, P is 6, and D is 10. Add them all up, you get 18. This is, again, where this can come in handy. You know, 2 goes per each dot, and you can count up the dots. The fourth, you've got S, P, D, and F. S is 2, P is 6, D is 10, and F is 14. Add them all up, you get 32. So within a given energy level, the numbers of the orbitals in an energy level may look like n to the second. The maximum number of electrons is 2n to the second. For the second energy level, n2, the number of orbitals is 2 to the second. So second energy level, second, 2 squared, there's 4. And then you're going to times that by 2, which gives you 8. I know this is a lot of math. This is another way you can figure this. The amount of electrons is basically 2n to the second. So you're just going to square the energy level and times it by 2. So for the third, there are 9 orbitals. So the third, so 3 squared, 3 times 3 is 9. 9 times 2 is 18. There are 18 possible in the third. Okay, so we do have some overlapping. We're not going to get too much into the overlapping because I really don't want to mess with it. That's what happens when you get to the 4th energy level. I really don't want to mess with it because it makes your brain go insane. So looking at this, 3 is normal. Once you get into 4, so you fill up 1, you fill up 2, you fill up 3D. But before you can fill up the 3D, you have to fill up the 4S. It gets really, really insane. And so I try not to go too much into it. Okay, so you could also do a diagonal rule of sublevel filling. So 1S fills first, then you do 2S, then you go across 2P, 3P. So if you were to write everything down, then you'd fill out 3P, then 4S, then 3D, then 4P, then 5S. See how it can get kind of confusing? And then you can see how I was going. 4D, 5P, 6S, 4F, 5D, 6P, 7S, 5F, 6D, 7P. It gets kind of insane. So, all right, we're done for right now. If you have any questions, please feel free to ask me, and I hope you guys have a great day.